video we going to discuss about the problem solved for radiation using different types of laws in radiation and emissivity problems. So this is a problem. A black body at 3000 Kelvin emits radiation. Calculate the following. First one is a monochromatic emissive power at 1 micrometer wavelength, and the wavelength at which emission is maximum emissive power, total emissive power. Calculate the total emissive of the furnace if it is assumed as a real surface having emissivity equal to 0.85. So given data T is equal to 3000 Kelvin, we need to find the monochromatic emissive power EB lambda at 1 micrometer and a maximum wavelength lambda max and maximum emissive power EB lambda max, total emissive power EB, emissive power of real surface epsilon is equal to 0.85. And this monochromatic emissive power from Planck distribute law, EB lambda equal to C1 lambda power minus 5 divided by E power C2 divided by lambda T minus 1, where C1 equal to 0.374 in 10 power minus 15 watt per meter square, C2 equal to 14.4 into 10 power minus 3 meter Kelvin, lambda equal to 1 into 10 power minus 6 meter, EB lambda equal to 0.374 into 10 power minus 15 into 1 into 10 power minus 6 power minus 5, and E values corresponding value we get it the EB lambda equal 3.10 in 10 power 12 watt per meter square. And maximum wavelength from wind displacement law, equation of wind displacement law is equal to lambda max T equal to 2.9 in 10 power minus 3 meter Kelvin. We substitute all values, we get it the lambda max is equal to 0.966 in 10 power minus 6 meter. And maximum emissive power of in this problem, we substitute the maximum emissive power equation EB lambda max is equal to 1.307 into 10 power minus 5 T power 5. And finally we get it the equation is 3.17 in 10 power 12 watt per meter square. And the total emissive power from the Stefan-Boltzmann law is equal to EB equal to sigma T power 4, where sigma equal to Stefan-Boltzmann constant 5.67 in 10 power minus 8 watt per meter squared Kelvin power 4, EB equal to 5.67 in 10 power minus 8 into 3000 power 4. So the final EB equal to 4.59 in 10 power 10 power 6 watt per meter squared. And the total emissive power of a real surface is EB real equal to epsilon sigma T power 4, where epsilon is emissivity 0.85 and EB real equal to 0.85 into 5.67 in 10 power minus 8 in 3000 power 4. So the EB real equal to 3.90 into 10 power 6 watt per meter square. And finally if we get it the EB lambda is equal to 3.10 and lambda max equal to 0.966. And this another problem, the emissivity of two large parallel plates maintained at 800 degrees Celsius and 300 degrees Celsius are 0.3 and 0.5 respectively. And in this problem we need to find about the net radiant heat exchange per square meter and percentage of reduction in heat transfer due to radiation shield and the temperature of the intermediate shield. So these all are the given data from this given problem. First we have to write about in the solution part, we mention from the data book we need to write about the parallel heat transfer data equation with the emissivity plate. Q is equal to epsilon bar sigma A T1 power 4 minus T2 power 4. And in this emissivity we substitute all values in the corresponding plate 1 to 2, we get it the one value of 15.88 watt per meter square. And similarly we have to follow this procedure for the another intermediate heat plates 1 to 3 or 3 to 2, we get it the another two equations like A and B. And finally simplify these equalize these both equations A and B, we get it the value of Q1 to 2B or Q2 to 3B, and substitute these all values in the given equation, we get it the heat transfer equation of 1.89 watt per meter squared Kelvin. And finally we substitute these all values in the heat reduction percentage. This is the formula of Q with the shield minus Q with the shield divided by Q without shield in the percentage. We get it the final percentage is 88%. And finally simplify this equation of A and B, we have to another intermediate temperature of the particular plate T3 will be mentioned in the temperature level of 911.5 Kelvin. Thank you.